Hello all, welcome to the video lecture 18 of group theory, and this will be the probably the final lecture in unit 2. So in this lecture we are going to see the number of conjugate classes in Sn. Special case we are considering group Sn, and we are going to see the number of conjugate classes in Sn. So before that, let us start with the definition. So we define what do we mean by a partition. So let n belongs to n, and we say that integers, positive integers n1 less than equals to n2 less than equals to and so on less than equals to nr is a partition of n, is a partition of n if we can write n as sum of this n1 plus n2 plus up to nr. So if we can write n as sum of these integers like this, positive integers, we say that it is a partition of n into r integers, right? And two partitions are equal, so this describes a partition of n, right, into r integers in r parts, and we say that two partitions are equal. Two partitions are equal. Two partitions, let us consider two partitions. So let the first partition be given by n1, n2, nr, and another partition be, let us say, n1 prime, n2 prime, and let us say ns prime. They are equal if first of all we have r equals to s. The number first of all it has to be same, and ni equals to ni prime for all I equals to 1 to r, right? R and r equals to s. Yes. So then we say that two partitions are equal if all this the numbers are same first of all, and the corresponding integers are also same, and we denote, let p of n denote the number of partitions of n, number of partitions of n. So let us count how many partitions of 1, 2, 3, 4 are possible. So for example, so if I consider n equals to 1, there is only one partition, 1. This is the only way to write 1. So p of 1, partition of 1 equals to 1. Similarly, if I take n equals to 2, so how many ways we can write 2? So we can write 2 equals to, so 1 is 2 and another is we can write 1 plus 1. So p of 2 is 2. Similarly, if I have, suppose, let us say n equals to 3. So in how many ways we can write n 3? So 3 can be written as 3, then 1 plus 2, and then 1 plus 1 plus 1. Right? So p of 3 equals to 3. Okay, so p of 1, the number of partitions of 1 is 1, but number of partitions of 2 is 2, number of partitions of 3 is 3. Then what should be, what is the guess? Number of partitions of 4. So 4 equals to 1 is this 4. Another way we can write as 1 plus 3. Another way we can write as 2 plus 2. 4 out and p of 4. What is the guess? P of 4 is, let us find out. So this is, and then this 2 we can write as 1 plus 1. So we have 1 plus 1 plus 2, and then all 1 plus 1 plus 1 plus 1. So how many such partitions are there? There are 5 cases. So 5, the number of partitions of 4 is 5, right? Similarly, check that p of 5, check whether you are getting 7 or not, and p of 6, check whether you are getting 11 or not, and so on. We can also check other, but I think up to 6 it is good to remember, and it is easier to compute by hand comparatively, uh, and then beyond 6 it becomes clumsy, right? We may miss some partition, or we may repeat some partition, so it becomes difficult, right? Now you must be thinking that what it has to do with Sn. So let us consider an example. A permutation in Sn gives a partition of n. A permutation in Sn gives a partition of n. For example, let us take theta belongs to S10, and theta equals to, we know every permutation can be written in as product of disjoint cycles. So let us write theta as, suppose this is 3 cycle, 1 2 3 1 3 4, then we have, let us say, 2 5 6, and we have 7 and 9. So from this we cannot conclude that theta is an element of S10, because 10 is missing. How do we know that it is up to 9? We are sure it is an element of S9, but here we are given it is an element of S10. So how does it give partition of n? How does it give partition of 10? What is partition of 10? First of all, let us recall the definition again. It is a set of all integers satisfying such condition such that their sum is n. So the sum must be 10. So, right? So, but here the sum is what? So here it is a 3 cycle. It is a 3 cycle. It's a 2 cycle. The sum is 3 plus 3 plus 2. That is 8. But we know that we can add also 1 cycles, single cycles. They are identity element. So we can either omit or add. It does not make change here in theta. So we write theta including all the 1 cycles. So write theta including all the cycles of length 1, if any. जो હોય તો અહીંયા તો છે, there are 1 cycles missing, right? So if any, if it does not have any 1 cycle, then it's fine. But if it has 1 cycle, we write them as including all the cycles of length 1 also, and also arranging in ascending order of the length of cycles. So we write theta is equals to 1 cycle. What are the 1 cycles missing? 8 is not there. So we write 1 cycle 8. Then 10 is also not there. So we can write 10. And then we have to write, so these are only 1 cycles, 8 and 10. So only 2 1 cycles. Then there is a 2 cycle. So which is at the end, but we write it before because we are writing in ascending order of their length. So 7 9. And then we can write 1 3 4. And then 2 5 6. Okay, or we can write this is same as 10 we could have written before, there is no problem. This one we could have written 9 7 also, that was fine. 7 9 9 7 is fine because transposition I j j I, it is same. 7 goes to 9, 9 goes to 7, so it is the same thing, one and the same thing. Here also 9 goes to 7 and 7 goes to 9, so it is the same thing. So that also we can change. We can change 1 cycles, but we are writing in ascending order. And this also we can change. We could have written 2 5 6 before and 134 afterwards, an equivalent way, that all we have seen. So let me keep as it is, 134256, or this also we can write as 256, and then 134 we can write as 341, or so any such representation is written. So what is the partition? So then theta gives the partition of 10s, then theta gives partition of 10 as 1 plus 1 plus 2 plus 3 plus 3. Then you can see this is actually 10, because all the 10 distinct integers are listed here, right? So if we omit single cycles, then we are not going to get 10. It is in S10, all 10 distinct elements we should get here. So it is a partition of 10. Now the question is, can two different permutation, so this is the question, can two different permutations give the same two different permutations in Sn? In Sn, suppose S10 we take another permutation, does it give the same partition of this? Is it possible? So that is the question, that it will it give the same partition, two different permutations in Sn give the same partition of n? That is a question, and if yes, then what is the relation between them? This is what we are interested in. So answer is yes, it is possible. Now find out any other permutation which give the same partition. Right? You can pause the video and find. I'll give you one example. So I have to give this partition. So I can take a cycle of length 1, another cycle of length 1, then a cycle of length 2, then 2 cycles of length 3. So I can take such kind of partition. So instead of this theta, I can write let us say sigma equals to, so in the notes I have written this example 7, 9. So there are two 1 cycles, but I am taking 7 and 9, and then I am taking 1, 2, then 3, 4, 5, 7, 9 are here, so we have 6, 8, and 10. So this partition of sigma also gives the same partition. Then sigma gives the same partition of 10s, right? So it is also 1 plus 1. There are two 1 cycles. Then one is a transposition, cycle of length 2. This is transposition. Then we have cycles of length 3, 2 cycles of length 3. So this is the same, and we can see that theta is not equals to, this is what we can see, theta and sigma are different. Why they are different? Because here the image of 9 is 7 and the image of 7 is 9, but here the image of 7 is 7, the image of 9 is 9, the image of 1 is 2, and the image of 2 is 1 here. But it is not the case. Here you can see the image of 1 is 3, here the image of 1 is 2. So even these two permutations are different, but they give same partition. So it is, so then the question is, what is the relation between them? So before that we define what do we mean by a cycle decomposition. So it is same as a partition. So let sigma belongs to Sn. We say that integers again bigger than equals to 1 and 2 and so on, and k, right? So that is less than equals to n. Of course it is in Sn, so largest cycle can be of length n only, not more than that, is a cycle decomposition of sigma. This is a cycle decomposition of sigma if we can write as if there are disjoint cycles. If there are disjoint cycles, sigma, we know sigma can be written as product of disjoint cycles. So if there are disjoint cycles of this length, first cycle of length n1, second cycle of length n2, and so on, disjoint cycles, sigma 1, sigma 2, up to sigma k in Sn with length of sigma I equals to ni, right? So for all I, for 1 less than equals to I less than equals to k, right? So with length this such that the two conditions should be satisfied. One is sigma can be written as product of sigma 1, sigma 2, and sigma k. So sigma can be decomposed into this cycle. So this gives a partition of 10 because it can be decomposed into cycles whose lengths are this, right? So sigma 1, sigma 2, sigma k. So that is the first case, and then n equals to, of course, it is a partition of cycle decomposition of s in Sn. So it gives partition of, so n equals to n1 n plus n2 plus nk, right? So this is the case. So what the question here was, what is the relation between two cycles giving the same partition? So our goal is to show that if two cycles give the same partition, then they are conjugates of each other, right? So that is our goal, that two permutation in Sn give the same partition if and only if they are conjugates of each other. If they are conjugates of each other, they give rise to the same partition. If they have the same partition, even if they are different, they are conjugates of each other. That is the target of today's lecture. So let me write what I said. So our next goal, which is the final goal of this unit, two permutations in Sn give the same partition of n if and only if they are conjugate of each other. Remember, conjugate being conjugate is an equivalence relation. So if A is conjugate of B, B is conjugate of A. So if and only if they are conjugate of each other. This is our next goal, and for this we consider, we should not say it lemma, but let us just write as it is. So or okay, let us write lemma. Karya sir has already written lemma in our notes, so we'll write let as it is. So suppose we have two permutations, sigma and theta, they are in Sn, such that sigma I equals to j, right, and theta of I equals to s, and theta of j equals to t. Then this implies theta inverse sigma theta of s equals to t. So what is meant by this? So this equivalently, this means sigma of I equals to j. This means that theta of I equals to s, theta of j equals to, we have written in Herstein notation, right? And theta inverse sigma theta. So theta inverse sigma theta. So we can write like this of s, right? Theta sigma yeah. So theta inverse sigma theta of s is applied here. So we better write theta inverse here, because theta inverse is applied on the first, so on the left in Herstein notation. So theta inverse, so theta sigma theta inverse of s equals to t. This is what we have to show, and proof is not difficult, but the meaning is important. Proof is very easy. There is nothing to prove. So sigma maps I to j. So what is s? So theta inverse. So s of theta inverse sigma theta at s ઉપર ઓપરેટ કરશે theta inverse sigma theta તો શું આવશે? So first s is applied, theta inverse, right? First this is applied, then sigma theta is there. And now what is theta inverse of s? So theta I equals to s. So theta inverse of s equals to I. So this is I, and we have sigma theta. Since theta I equals to, theta of I, here theta of I equals to s, this implies theta inverse operated on s. So we are writing the argument on the left hand side, just like Herstein, equals to I. So this is I, and so what is this? This is sigma of I, and theta. So what is sigma of I? Sigma of I is given, so this is j, right? So since sigma of I, so I sigma is j, this is given, and theta j. And what is theta j? That is also given, this is t, since theta of j equals to t. Okay, so if sigma sends I to j, then theta inverse sigma theta sends s to t. That's it. See, but what is the meaning? So meaning I am writing here, if sigma sends I to j, then theta inverse sigma theta sends, what is sends s to t, right? It sends s to t, but what is s? S is nothing but theta I, and what is t? T is nothing but theta j. So then if sigma sends I to j, we can say that theta inverse sigma theta sends theta of I to theta of j, or in other notation we can write I theta to j theta. So sigma ની ઇમેજમાં, સિગ્મા જો I ની ઇમેજ j હોય સિગ્મામાં, તો થીટા ઇન્વર્સ સિગ્મા થીટામાં શું થઈ જશે? અહીંયા થીટા એપ્લાય થઈ જશે. થીટા I will go to theta j, right? So this is very simple, and converse is also true. So this is if and only if. Converse is also true. If theta inverse sigma theta of s equals to t, so s એટલે શું છે? S એટલે conversely s theta inverse sigma theta. So this is s એટલે is nothing but theta I. S we know this is theta I. Again look at this. મને થોડું કન્ફ્યુઝિંગ જેવું લાગે છે, મને ખ્યાલ છે આવું થાય છે, બટ મને કન્ફ્યુઝન નથી. Just see, read again. I write the conclusion, then it will be clear. So then that is sigma, and so suppose this equals to t. ઊંધું જો થતું હોત, સપોઝ અહીંયા હોત તો શું થાત? તો પણ sigma sends I to j, we can say that sigma sends I to j. So let me not use this. So suppose this is t, so then what is s? S equals to I theta, theta inverse sigma theta equals to t, since theta of I equals to s. But then this is theta theta inverse, so this is I sigma and theta and t. What is t? T is nothing but theta j. T is nothing but theta j. So this is j theta. So since t equals to j theta, and since theta is 1 1, આ બધા તો permutation છે ને, 1 1 function છે, so that means sigma I equals to j, since theta is 1 1. બહુ આમાં proof જેવું કંઈ છે જ નહીં, sir. This is not the proof. Proof is only this much that we have done. So there is nothing to, but converse part also we are just looking into. And so what is the conclusion? If sigma sends I to j, this is the conclusion, then theta inverse sigma theta sends theta I to theta j. This is our conclusion, right? So let me write that remark again. Whatever we have written, this one I write again here as a remark. So first one, if sigma in Sn maps I to j, then importantly, then its conjugate. આનો conjugate શું થાય? આનો conjugate, what is a conjugate of A? If B is conjugate of A, then we know B equals to C inverse AC. So conjugates of A are of the form Y inverse AY. So આનો sigma નો conjugate શું થાય? તો કે theta inverse sigma theta, and what that will do? That will maps theta of I to theta of J. So that is theta of I ને આપણે આવી રીતે પણ લખી શકીએ I theta to J theta, right? So sorry. So if sigma sends I to J, what does its conjugate do? Conjugate doesn't do anything except theta apply થઈ જાય. Sigma માં I ની ઇમેજ J આવે તો theta inverse sigma theta માં theta I ની ઇમેજ શું થઈ જશે? theta J થઈ જશે. એનો મતલબ કે જે સાયકલ હશે, સાયકલ્સ ઓલ વિલ બી નોટ ડિસ્ટર્બ. સાયકલ્સની લેન્થ એવડી ને એવડી રહેશે. સો that is the second remark. If I1, so I can write not if but if and only if I1 I2, let us say IR is a cycle of sigma, then suppose this is cycle of sigma ની અંદર r length વાળી cycle છે, તો આના conjugate its conjugate will have what kind of cycle? So its conjugate will be theta inverse sigma theta. So what will be the effect? If I1 goes to I2 in sigma, then theta inverse sigma theta શું કરશે? It will map theta I1 to theta I2. If I2 goes to I3, then this will in under sigma, then what this will do is theta inverse sigma theta, it will map theta I2 to theta I3, and so on, theta IR. So even if we don't write this is fine. Clear? Once again I am repeating, you can go back and repeat whatever we have discussed. So if what does sigma do? If this is cycle of sigma, એનો મતલબ કે sigma I1 શું થશે? I2 થાય. તો આનો conjugate લીધો with respect to theta inverse sigma theta, તો શું કરશે? તો કે sigma જો I1 ને I2 માં send કરતું હોય, તો this will send theta I1 to theta I2. Similarly, I2 goes to I3, then theta I2 goes to theta I3, and so on. So if this is a cycle of length r, then this is also an r cycle. Right? So this is an r cycle in sigma, then this is an r cycle, is a cycle of its conjugate. So this is a conjugate of sigma. See, એનો મતલબ કે if sigma has whatever decomposition, sigma નું decomposition લો cycles માં whatever length, તો એના conjugate માં same decomposition will be there in the conjugate, right? Because it is not going to change the length, but is just applying theta inside the cycle. So that is only, so that means two conjugates will have the same decomposition. This is our conclusion here. Is it clear? Once again we go back where we started. I know this is a video, so you can go back again on your own, but let me recall what we have done. So partition of n is any natural number, and then we have set of positive integers is partition of n if they are written in ascending order and their sum is n. When two partitions are equal, that is clear. So Pn is the total number of partitions. So P of 1 is 1. There are only one way to write 1. There are two ways to write 2. There are three ways to write 3. There are 5 ways to write 4. So in this order. So P of 5. So P of 4 is 5. Partition number of partitions of 4 is 5. Similarly, check number of partitions of 5 is 7. Check number of partitions of 6 is 11. Try to list all possibilities. If you are getting 10, you are missing 1. So that's how you get all 11. If you are getting more than 11, that means you have somewhere you have listed some entry multiple times. So this is what we have seen. Now the thing is how it is related to Sn. So every permutation gives rise to a partition. How? So every permutation we know can be written as product of disjoint cycles. Now in this product we may have omitted one cycle. So include all those one cycle and arrange them in ascending order of the length of cycle as we see here. Arrange them, it doesn't matter if you are writing in different representation, but arrange them in the length, ascending order of length. So one cycle, all one cycles are over, then we take two cycle, then we can take three cycle, you can interchange, no problem. So length is 1 plus 1 plus 2 plus 3 plus 3, so that is 10. So this is a permutation in S10, it gives a partition of 10. So a permutation gives a partition, right? Permutation in Sn gives a partition. Now the question is whether two permutation will have the same partition. Yes. See, one we have given example. It is just partition only. है 1 plus 1 plus આવું જ હોવું જોઈએ. So here also it is 1 plus 1 plus 2 plus 3 plus 3. There is nothing new here. But these two are different permutation because here the image of 1 is 3, as you can see, and here under sigma the image of 1 is 2. So these two are different partition. So that means two different permutations can give rise to same partition. So then what is the relation between those two permutations? So that relation, they must be conjugate. That is the converse part. What we have seen here actually, if they are conjugate, they give the same partition. So for that, what do we mean by cycle decomposition? So say this integers is cycle decomposition of sigma. If sigma can be written as product of disjoint cycles sigma 1 to up to sigma k, so that each of has length ni, sigma 1 has length n1, sigma 2 has length n2, and sigma k has length nk, and total is n. So this is sigma. So what is cycle decomposition of sigma? This is cycle decomposition of sigma, which is nothing but partition. So partition is, because sigma can be written as one cycle, so this is sigma 1. What is length of sigma 1? It is 1. This is sigma 2. What is length of sigma 2? This is 1. This is sigma 3. Length of, so sigma can be written as product of sigma 1, sigma 2, sigma 3, sigma 4, sigma 5. And length of all these are 1 plus 1 plus 2 plus 3 plus. So their sum is 10. So that is cycle decomposition of sigma. So cycle decomposition of any permutation gives rise to a partition, which is nothing but a partition. And now what we are going to show, that two conjugates will have same partition. So for that, in fact, even only if we are going to show, for that, this is the lemma we have stated as lemma, but this is just an observation. Suppose sigma is a permutation, so sigma I is j, right? Then what says that if sigma sends I to j, then it's conjugate with respect to theta. A na conjugate કેટલા હોય? તો કે y inverse ay, this is a conjugate of a. X inverse ax, this is also conjugate of a. C inverse ac, this is also conjugate of a. So this is conjugate of a with respect to y, this is conjugate of a with respect to x, this is conjugate of a with respect to c. So sigma is given, right? And we are given that sigma sends I to j, this much is given, and theta is given. So we can form conjugate of sigma with respect to theta inverse sigma theta. So what does it do? It will send theta of I to theta of j. So let us call theta of I as s and theta of j as t. So what does it do? It sends s to t. That means it sends theta of I to theta of j. Very simple. So conjugate kai nathi karta. So that is the observation, that cycle decomposition will remain same. Sigma ma jo jetli cycle hase ne evi j theta inverse sigma theta, the length will be same. What it will do is just it will map it, theta will be applied. So then the proof is very simple. Converse also is true. So the two observation, if theta maps I to j, sigma maps I to j, then theta inverse sigma theta maps theta I to theta j. So if sigma has an R cycle, sigma ni અંદર R cycle હોય તો એના conjugate માં પણ R cycle જ હશે. The length will never change. What changes is that if I1 goes to I2, then here theta I1 goes to theta I2. Theta is applied. There is no other change. So that means cycle decomposition remains same. So two conjugates give the same cycle decomposition. So that is after this remark, we write this as a corollary. What we have seen is that let sigma belongs to Sn, then every conjugate of sigma, has the same cycle decomposition as that of sigma. Right? So two conjugates give the same cycle decomposition because conjugate is doing nothing. If I take conjugate of sigma with respect to theta, in the R cycle, whatever the cycle of sigma is there, length will remain same, only theta will be applied. If I take conjugate of sigma with respect to, let us say, psi inverse sigma psi, what it will do? This R cycle, if it is R cycle in this, then its conjugate will give another R cycle, which is I1. Psi I1 equals psi I1 is mapped to psi I2, and so on. It is mapped to psi IR. So R cycle will remain same. Only the thing is that psi will be applied. So the conjugate basically doesn't do anything. It just applies. So length remains same, and as soon as the length remains same, the partition is same. So if I am taking any conjugate of this, so length will remain same. So length remains same. So 1 plus 1 plus, so the partition will remain same. So two conjugate permutations have the same cycle decomposition, or in other words, have the same partition of n. So this is what we have seen. Okay, let us consider an example. Let us take an example. Suppose for sigma equals to, let us say 4, 5, and 1, 2, 3. So this is sigma, and theta equals to, let us say 2, 4, 1, and 3, 5, 6, 7. These are in S7, right? So compute the conjugate of sigma with respect to theta. So that is what we have to compute. Theta inverse sigma theta compute karvanu. See, they are not conjugates. Sigma theta, they are not conjugates. Sigma is given, theta is something else, and conjugate of sigma with respect to theta. So A is given. What is A? Sigma. What is conjugate of A? Is not C, it is B. B equals to C inverse AC. So C is not conjugate of A. What is conjugate of A? B is conjugate of A. So sigma is given here, and theta is given. Theta is not conjugate of A. What is conjugate of A? Theta inverse sigma theta. So we have to compute this. So what is theta inverse sigma theta? So theta inverse sigma theta is nothing but if sigma sends 4 to 5, then we know this will send theta 4 to theta 5. Writing this way, I can also write this as theta of 4 to theta of 5, just using Herstein notation. Right? So this cycle will remain same, and this sends 1 to 2, 2 to 3, and 3 to 1. So this will be, theta will be applied. Theta 1 will be sent to theta 2, theta 2 will be sent to theta 3, and theta 3 will be sent to theta 1. So now we can compute what is this. So what is theta of 4? Theta of 4 is 1 here, you can see. Yes. So this is 1. What is theta of 5? Theta of 5 is 6. 5 goes to 6. So this is transposition 1, 6. And theta of 1. Theta of 1 is 2. So this is 2. Theta of 2. Theta of 2 is, sorry, not this. Theta of 2 is 4. Right. So this is 4. And theta of 3. Theta of 3 is 5. This is how it is computed. So this is just an example for you to understand. એક સિગ્મા આપેલું હોય અને બીજું permutation આપેલું છે, તો with respect to that, what is the conjugate? So theta inverse sigma theta is a conjugate of sigma. So conjugate of sigma is this. So these two are conjugates, sigma and theta inverse. So you can see this is, what is the partition of sigma? Sigma has partition 2 plus 3. So its conjugate also has partition 2 plus 3. because nothing, it does nothing but actually theta is applied. Okay, and similarly I ask you to compute this. So as an exercise, not this is not exercise, but just compute. I can, for your practice. Now suppose theta is given. Compute the conjugate of theta with respect to sigma. So compute the conjugate of theta with respect to sigma. What is a conjugate of theta with respect to sigma? This will be sigma inverse theta sigma. So you have to compute sigma inverse theta sigma. And what is the partition of theta? Theta has this partition. Oh, actually, this is not correct partition. Uh, yeah, you can write as here. This is fine. 3 plus 4. So this also will have 3 plus 4. Check this. But this is not correct partition of 7. 2 plus 3. We have 1 plus 1. So 7. 1 cycles are missing, right? Here. I didn't check, so we have to check. 1 cycles are missing. Here also we'll have 1 plus 1 plus 2 plus 3. So what are the missing cycles? Let us write those missing cycles. So here what is missing is 1, 2, 3, 4, 5. So 6 is missing and 7 is missing. So we can add here 6 and we can add here 7. Of course, we write in ascending order of length. So we write single cycles before, then 2 cycle 4, 5, then 1, 2, 3. Here also we can write so 1 is there, 2 is there, 3 is not there. So we can write 3 here, 4, 5, 6, and then 7 is missing. So 7. So this is actually partition. So they have the same partition. Here the partition is 3 plus 4. Of course, 3 plus 4 is 7. So here also we have 3 plus 4. So what will be in fact sigma inverse theta sigma? Nothing but इसमें sigma apply कर दो theta में. तो ये क्या होगा? I'll give you a hint also. So this is nothing. Let me write here. Sigma inverse theta sigma क्या होगा? So what it does, as we have seen before, theta में sigma apply कर दो. So if theta में 2 for 1 cycle है, so here we'll have sigma 2, sigma 4, sigma 1. This is the cycle. And sigma 3, here we have cycle 4, cycle 3, 5, 6, 7. So we have sigma 3, sigma 5, sigma 6, sigma 7. अब आपके लिए कुछ छोड़ नहीं रहा हूँ, मैं सब कर दे रहा हूँ. ठीक है, आपको कुछ करना नहीं है, बस वीडियो देखो. आप अगर देख ले तो काफ़ी है. Yeah, because and then we'll see this again, but I'm not going to discuss these silly things in detail in Google. This is our Meet lecture. So the same. So this is nothing but we just another notation. So what is this? Okay, so sigma of 2. Sigma of 2 is 3. 2 goes to 3 in sigma. Then sigma of 4. 4 goes to 5 here. So this is 5. Sigma of 1. Sigma of 1 is 2. And then complete this cycle. Let us complete only. Won't take much time. So sigma of 3. Sigma of 3 is 1. Sigma of 5 is 4. Sigma of 6. 6 तो इसमें है ही नहीं. 6 is here. So sigma of 6 is 6. Sigma of 7 is 7. Right, so this is conjugate. So as you can see here also we have a partition as just like theta, because only sigma is applied, length is not changed. Right, so we have a partition 3 plus 4. Okay, so what we have proved so far, only one thing. We have considered a lot of examples, and so one thing we have proved is if two permutations are conjugate of each other, they have the same cycle decomposition, because the length of cycles are remaining same by the conjugate also. It is just whatever theta suppose we are taking with respect to theta, then theta is applied. With respect to psi, if we are taking the psi is applied in the cycle, length of cycles remain unchanged. So two conjugates give rise to the same permutation. So this is our result, right? if sigma is in Sn, every conjugate of sigma has same cycle decomposition. Cycle decomposition is nothing but the partition of that n. Okay, so this is the first one, and now the second one. So this is another corollary. It says that if two permutation have same cycle decomposition, now it is converse, then they are conjugate of each other. So if sigma and psi have the same cycle decomposition, then they are conjugate. Again, the proof is not difficult, it's very easy. So suppose let us fix that they have the same cycle decomposition. So let us take 1 less than equals to n1 less than equals to n2 and so on less than equals to nk be the cycle decomposition of both, be the cycle decomposition of sigma and psi. So we can write sigma and psi as, so suppose sigma has cycle decomposition, so first integer is n1, and matlab sigma has a cycle of length n1, so we can write i1 i2 in1, right? And second integer is n2, so that means it has a second cycle of length n2. So here we have I n1 plus 1 and so on up to I n1 plus n2 બરાબર 1 થી start કરીને n2 સુધી. So this is a cycle of length n2 and so on. Last વાળું શું હશે? This is I1 I n1 plus I nk minus 1 and up to n, which is nothing but this is sum of I1 plus I2 plus I nk, I n1 I n2 and I nk. Yeah, so n is n is, yes, so that is n, right? Length is k, so here the length is n1, here the length is n2 and nk. So I cannot write like this, it is n, just you can understand, this will be n. So what is the length of this one? So length of this one is n1, then here again from 1 to n2, n1 plus 1, n1 plus 2, n1 plus 3, n1 plus n2. So the length is here, this is n2 and so on. Finally the length is here, it is nk, and the total n1 plus n2 plus this, it's a cycle in Sn, right? So I have not written cycle in Sn, so they are a cycle in Sn, so total is n, sum of this all, this is going to be n. And similarly psi also has, let me add one more page here. Okay, yeah, so and psi also has similar decomposition because we have assumed that they have the same cycle decomposition. So suppose psi can be written as, suppose j1 j2 and jn1, and this is jn1 plus 1, jn1 plus n2 and so on. Finally here also j1 jn1 plus jn2, sorry, jn1 plus plus nk minus 1 to n. So suppose this also has, so both of them have the same cycle decomposition. Here also we have n1, here we have n2 length, and here we have nk. Suppose they also both have same cycle decomposition. what we have to show, these two are conjugate of each other. Conjugate मतलब શું થવું જોઈએ? If they are conjugate of each other, we must find. So to show that sigma, psi is a conjugate of sigma, so to show that psi is a conjugate, I'm explaining all this, but this is no need, it is very simple. Conjugate of sigma, we have to find some theta. So I'm writing all this, whatever I am explaining, in written. In proof, one need not write all this. This is just explanation part to show that they are conjugate of each other. So one is conjugate of the other, or other is conjugate of conjugate equivalence relationship, symmetric to hase. To show that psi is conjugate of sigma, we have to find some theta such that. So we have to find theta such that psi equals to theta inverse sigma theta. આવું થઈ જાય તો we can say that these two are conjugates of each other. Psi is a conjugate of sigma. Right? If we can find theta. So how do we define? So define theta by so theta which sends I1 to J1, theta sends I2, theta of I2 equals to J2, and so on. So that means theta of IT equals to theta of JT for all t. Right, so this is how we define theta. What is theta? Theta is theta j it equals to theta it equals to jt, not this. Yeah, theta it goes to jt. So I1 goes to j1, I2 goes to j2, and so on. In1 goes to jn1, then in plus 1 goes to this. So like this, we map all this. Right, so then what is our claim? Claim is that then psi is conjugate of sigma. That means psi equals to theta inverse sigma theta. Psi to apne khabar, psi we know, psi is clearly defined like this. J1 goes to J2, J2 goes to J3, and so on. So what about psi? Psi we know, so we have to just check this one only. What is theta inverse sigma theta? So since then clearly I can explain. So then clearly theta inverse sigma theta equals to psi. Why? This is the reason. I1 goes to I2, sigma sends I1 to I2, agreed? So conjugate of sigma, theta inverse sigma theta, what it does, it will send theta I1 to theta I2. Okay, let me write that if you have got that. So this is the explanation part, just for our understanding. All this stuff are so trivial that it takes time to understand, so there is nothing to prove here. So for explanation, sigma maps I1 to I2. So then we know theta inverse sigma theta maps theta I1 to theta of I2. But what is theta of I1? Theta of I1 is we have defined J1, so it maps J1 to J2. So this maps I1 to I2, it maps J1 to J2. Sigma maps I2 to I3, it will map J2 to J3. What is that? J1 goes to J2, J2 goes to J3. This is nothing but it is psi. It is psi. Right? So that therefore, and psi maps J1 to J2. So for every such thing, theta inverse psi theta, this will be equal to psi, because they are same. J1 goes to J2, here also J1 goes to J2. So as far as explanation is concerned, one can just understand this. So just map kar devan. right? To show that if they have same cycle decomposition, they are conjugate of each other. Take the first cycle, n1 length, map each element corresponding, n2 length, map each of the elements corresponding. Then that theta inverse sigma theta is nothing but it will be psi. So then, so what we have proved is if we combine these two together, so the theorem from what we have discussed. So all this is kind of a discussion. There is no much lengthy or rigorous proof about this. Of course, the proof is rigorous, but it is just kind of explanatory proof. There is no much theory involved here. So what we have proved from this, combining all this, two permutation in Sn have the same cycle decomposition if and only if they are conjugate of each other. So first we have proved, suppose they have same cycle decomposition. So two conjugates will have same cycle decomposition, because conjugate will do nothing, but that theta will be applied. If sigma is an permutation, its conjugate theta inverse sigma theta will change nothing. The R cycle will remain as R cycle only, just theta will be applied. So two conjugates have same cycle decomposition, that means same partition, and conversely same partition way. If they have the same partition, so this is n1, n1, n2, n2, so the partitions are same, then they are conjugates. How to show that they are conjugates? Just map corresponding elements of all those cycles. So combining this, we can write two permutations. Two permutations in Sn have the same cycle decomposition, if and only if they are conjugate of each other. Right, and from this is from what we discussed above. Combining all those two corollaries and lemma, we come to this conclusion. So you see, this type of examples are asked in NET also, and NET and NBHM know whether these two are conjugate of each other or not. If they are conjugate of each other, find that theta. So we now know how to find theta, right? Okay, so finally, how many conjugates are there? This is the main result what we are looking for. So the number of conjugate class in Sn, બે સેમ પાર્ટીશન આવે તો બે એકબીજાના કોન્જુગેટ હોય, બે એકબીજાના કોન્જુગેટ હોય તો સેમ પાર્ટીશન આવે. તો પછી અલગ અલગ કોન્જુગેટ ક્લાસ કેટલા થાય? હાઉ મેની ડિફરન્ટ કોન્જુગેટ ક્લાસ વિલ બી ધેર? So if two are conjugate of each other, they are in the same class, they will give the same partition. If they are in different class, that means they are not conjugate of each other. That means they are giving two different partitions, because if partitions are same, cycle decomposition is same, cycle, they are conjugates. If they are conjugate, cycle decomposition is same. So if they are in the same class, they will have same partition, cycle decomposition. If they are not in the same class, that means they must have different cycle decomposition. If they have different cycle decomposition, they are not conjugates of each other, based on this previous result we have proved. So how many conjugate classes are there? Ketla classes hase? So as many as partitions of n are there. So that is the result. So the number of, this also is asked in NET. This such type of questions are asked. The number of conjugate, and it was asked about S6. S6, how many conjugate classes are there in S6? So that is partition of 6, which is why I wrote there it is up to 6. It is important to remember. There are 11 partitions of 6. So the number of conjugate classes in Sn is nothing but Pn, that is the number of partitions of n. And suppose if we want to write the proof, we can write the proof of this. So we have seen that two permutations give unique cycle decomposition. So we have seen that a permutation, given a permutation, it has a permutation gives unique cycle decomposition. That is nothing but cycle decomposition is nothing but a partition. So permutation gives rise to a partition, nothing but a partition of n. So permutation in Sn will give rise to a partition of n, right? And two conjugates give same cycle decomposition. So two conjugates. So if we have two conjugates, they give same cycle decomposition. That means the same partition. Two conjugates give the same cycle decomposition. That is the same partition. So two conjugates never give a new partition. So एलिमेंट લઈએ એક પાર્ટીશન મળે, સામે પાર્ટીશન લઈએ તો એક એલિમેન્ટ મળે પરમ્યુટેશન, એ જેનું ડીકમ્પોઝિશન એ પાર્ટીશન હોય. That is also true. Yeah, once again I have added a page, so it started from beginning. Yeah, conversely, so દરેક permutation છે, દરેક permutation એક partition આપે. If two permutations are conjugate, they give same partition. Conversely, if you take a partition, there is a permutation whose decomposition is that. So conversely, if 1 less than equals to n1 less than equals to n2 and so on less than equals to nk is a partition of n. Suppose this is a partition of n, then we can define sigma, then define sigma equals to, we can define like this, 1 2 1 goes to 2 up to n1, and then n1 plus 1 up to n1 plus n2 and so on. So last one will be n1 plus n2 plus nk minus 1, and that goes up to n. So n1 length wadi cycle, so that is first n1 elements, then n2 length wadi cycle, that is here it is n2, this is n1, and this is nk. So if we are given a partition, we can always find a permutation whose cycle decomposition is same as, so then the cycle decomposition, then cycle decomposition of sigma is n1 n2 nk, which is partition of n, because the sum is n, which is a partition of n. So this is a partition of n we started. So if partition is given, we get a permutation which has same cycle decomposition. So partition of n અહીંયાથી તો સ્ટાર્ટ કર્યું હતું, એટલે આની જરૂર નથી, રાઈટ. So partition આપેલું હોય તો permutation મળે whose cycle decomposition is that partition, and if permutation is given, we have cycle decomposition. But two distinct permutations may have same cycle decomposition, because if they are conjugates of, if and only if they are conjugates of each other. So how many distinct such partitions will be, how many distinct such conjugate class will be there? That is nothing but number of distinct partitions of n. So thus the number of conjugate class of Sn thus the number of conjugate class of Sn, classes of Sn, is same as the number of partitions of n. કોઈ ખાલી નથી રહેતું. ઇફ પરમ્યુટેશન હોય તો પાર્ટીશન મળે. કોઈ એવું પરમ્યુટેશન નથી જેને પાર્ટીશન ના મળે, કોઈ એવું પાર્ટીશન નથી જેને કરસ્પોન્ડિંગ પરમ્યુટેશન ના મળે. સો અને એક પાર્ટીશન લઈએ તો બધા કોન્જુગેટ એમાં જ આવી જાય, એટલે એક કોન્જુગેટ ક્લાસ એક પાર્ટીશનથી થાય, બીજો કોન્જુગેટ ક્લાસ બીજું પાર્ટીશન આપે. So how many such distinct class will be there? This is nothing but this. So finally we end this lecture with an exercise. So this is the exercise. It is given in Herstein also. Some discussion is given at the end of the section, and I have listed in my notes also this as exercise. So find the number of elements in the following. First is C of sigma, N of sigma, where sigma is a transposition in Sn. Two cycle ના conjugates કેટલા હશે કાઉન્ટ કરવાનું, two cycles ના normalizer માં કેટલા elements હશે કાઉન્ટ કરવાનું. Find the number of elements in conjugate class of sigma and normalizer of sigma transposition, where sigma is a transposition in Sn. And similarly C theta n theta, where theta is n cycle of full cycle of length n in Sn. Okay, so if you need some help with this, you can refer to the text Herstein, it is given. And we have seen, hint is, I can give you the hint. We have seen this CA, there is 1 correspondence to G quotient NA, that is small ca, the cardinality we know, small ca is equals to order of G upon order of NA. So if we know the number of elements in conjugate class, we can find the number of elements in normalizer, just divide by this, right? If we know one of them, we can find the other. So that is the hint, and here we stop. So that is the final lecture of this unit, and this completes this unit. So next class we start with unit 3, which is very important. So we have covered more than 50%, because these two units are the largest ones, and then they are just in the decreasing order. So unit 3 is Syllabus theorem, which is important. See you tomorrow in the class.